Okay, well, thank you everybody for coming. Today we are very privileged to have Baha Balantekin speak about quantum entanglement in neutrino many-body systems. So Baha, let me just give you some details. So Baha is Eugene Wigner Professor at University of Wisconsin-Madison, and he's won numerous awards, including he's an American Physical Society Fellow. He's the DNP Distinguished Service Award winner, and he has numerous other awards, such as the Senior Scientist Award from the Alexander von Humboldt Foundation. And he's done extensive work in neutrino systems, quantum many-body systems, all things interesting. So you'll hear about many of these things in this talk today. Thank you, Baha.
Thank you. Thank you for inviting me, and it's great to see a lot of old friends. I'm going to talk today about quantum entanglement and how they play in neutrino many-body systems. Well, neutrinos from astrophysical objects is not a theorist's hypothesis. Actually, neutrinos had been observed from the core collapse supernova 1987A. And as you can see on the left of the transparency, you see that suddenly the dashed line is the background in Japanese, and you can see that suddenly there is an increase in the neutrino flux, which of course decays as time goes on. And this flux had been observed by three detectors, which were operating at the same time. The basic mechanism is relatively easy to figure out. You start with a progenitor star, which has mass of 8 times the mass of the sun at least, but more like more than 12 times mass of the sun. The energy released is also relatively easy to figure out. It is the entire gravitational binding energy of the pre-supernova star, which is 10 to the 53 ergs or 10 to the 59 MeV. And of course, during the star, you end up with a very hot protoneutron star, which would like to cool. And the best, the simplest, the most efficient mechanism for it to cool is by emitting neutrino-antineutrino pairs. And 99% of this energy is carried away by neutrinos and antineutrinos, which basically have energies which is the representative of the temperature of the protoneutron star of the order of tens of MeV. So if you look at the numbers together, you figure out that there are 10 to the 58 neutrinos produced in this collapse. And of course, they make it, and they make it to Earth, and they had been observed at least coming from supernova 1987A. Well, 10 to the 58 is a huge number. So once you go to such densities, you can no longer get away describing neutrinos using only one-body interactions. Of course, the one-body interactions for the neutrinos had been around a long time. Ordinary neutrino oscillations is a one-body phenomena in the language of many-body physics. The so-called MSW effect is again a one-body phenomenon because it takes the background and then calculates it in the Hartree approximation, and you're moving in the mean field created by the particles in the background. But as soon as you have 10 to the 58 neutrinos, you have to include the effects of neutrino-neutrino interactions. So then that makes the problem a one and two body problem. And of course, as we all know, a one and two body many-body problem is not that easy to solve. So the second term that is added coming from this extra neutrinos makes the core collapse supernova a very interesting many-body problem, which is driven by weak interactions, and it leads to novel collective and emergent effects, such as conserved quantities and interesting features in the neutrino energy spectra called swaps or splits, which I will illustrate in a few minutes. Of course, this is from the neutrino physics perspective, a very interesting phenomena, but also from the perspective of nuclear physics in areas, for example, that EFRIB is very much interested in. It also is very closely related to the origin of elements. At the moment, we do not know where elements are formed, especially where our process is happening. Well, we know that the Big Bang makes just a few of them, and some of them can be made in the oldest stars, our process, RP process, new process, and so on. But like, for example, we do not know at the moment the location of the R process, could be supernova, could be neutron star mergers, and so on. But all these environments where elements are produced also have abundant number of neutrinos. Neutrinos not only play a crucial role in the dynamics of these sites, but they also control the value of electron fraction. Because neutrinos can interact with neutrons and protons, electron fraction is the same as proton to neutron ratio. And of course, that ratio is the determining parameter for the yields of element synthesis. So it's really important to understand what neutrinos do, how they propagate in these environments. It's really important to understand all those if you want to look at element formation in detail. So there are a lot of questions that you need to answer, and these have to be answered both theoretically and experimentally. So for example, the neutron star has a very high density in it, so you have to know the high density equational state. Neutrinos remain trapped for a while, so you have to know the interactions, the properties of weak interactions inside the high density equational state. And then eventually they decouple, they oscillate. These can be flavor oscillations or they can be collective oscillations. That is the main topic of this talk. And they reach a region where you have possibly neutrino heating of the shock or element synthesis, nucleosynthesis. And of course, there, those two reactions that I write, electron neutrinos on neutrons and electron antineutrinos on protons, those two reactions determine the neutron to proton ratio. And that neutron to proton ratio depends on relative intensities of electron neutrinos and electron antineutrinos, which in turn depend on neutrino oscillations. So then if you understand the neutrino oscillations as neutrinos travel from the neutron star to the location of the nucleosynthesis, you really need to include that in understanding nucleosynthesis. Finally, of course, you detect them on Earth. At the moment, there are a number of detectors. These are the most prominent in the US is the Dune detector, which is going to use a liquid argon. So, well, you know, neutrinos at the MeV range on a nucleus is the business of nuclear physics. And there are a lot of questions that you have to think and answer both theoretically and experimentally there. And of course, there are other detectors like scintillators, which have a lot of carbon, and Wadar-Cherenkov detectors, which have a lot of oxygen. They all need input from the nuclear structure physics. Now, the neutrino system, neutrino many-body system in these astrophysical phenomena is the only many-body system driven by the weak interactions. If you think about the many-body systems, nuclei is driven by really the strong interactions, and you can have at most order of 200 particles. The heaviest stable nucleus is lead-208. In the condensed matter type many-body systems, the interaction is driven by the electromagnetic interactions. The system is driven by the electromagnetic interactions. You have at most an Avogadro number of particles, but in most practical applications, the numbers are a lot smaller. Whereas neutrinos in supernova is a system driven by weak interactions, and it includes the most number of particles, 10 to the 58 or so neutrinos. So this is an illustration of the fact that astrophysical extremes allow us to test physics that you cannot test in any other ways. And I should point out that this neutrino-neutrino interaction in the supernova is within the standard model. It's not new physics, it's not beyond the standard model physics. It is the last part of the standard model physics that has not been directly tested. In order to talk about this, I'm going to introduce the neutrino flavor isospin. Just basically, electron neutrino is spin up and muon neutrino is spin down if you take two flavors. Of course, if you take three flavors of neutrinos, you have to introduce SU3, which gets more complicated, straightforward but complicated. And I will introduce creation annihilation operators since I want to use the language of many body physics. So A E dagger, for example, is the operator that produces an electron neutrino, and A mu is an operator that annihilates a muon neutrino. And then from those, you can form this isospin SU2 algebra that's written there. And then you can write down for example, oscillations of neutrinos, free neutrinos, neutrino oscillations in that form as shown there in terms of these J plus, J minus, and J0. Or you can also write, for example, the MSW effect as shown at the bottom of the slide, interacting with the background of electrons calculated using Hartree approximation in the background, using the background electrons. Now, I had written these Hamiltonians using the SU2 operators. The reason is I want to eventually think about the cases where you have more than one neutrino. But if you have a single neutrino, of course, these SU2 operators can be replaced by the Pauli matrices. And then these Hamiltonians are the Hamiltonians that you see in the particle physics papers describing these effects. But this is a slight generalization of that. So including neutrino-neutrino interactions then brings a term which is of the form J dot J. And the coefficient of that term is 1 minus cosine of the angle between the momenta of the two neutrino interacting. And of course, you have to include the one body term as well, as shown at the bottom of the transparency. While the one body term, of course, has the oscillations of neutrinos and interaction with the background electrons, the MSW effect. To write down the interaction, oscillation of neutrinos, one introduce a fictitious sort of quote-unquote magnetic field B, so that it looks like an NMR problem, but you don't have to. That fictitious vector is given there. X component is sine 2 theta. Y component is 0, and Z component is minus cosine 2 theta. So this is the problem that we need to solve. Now, of course, so far I only had neutrinos. You can include antineutrinos quite easily. You can also include three flavors. Both extensions are actually quite straightforward, but quite tedious. And if you are interested in those details, they are given in that paper shown there. Now, this problem is exactly solvable in the single angle approximation. Exactly solvable doesn't mean it's easy to get the solutions. Exactly solvable is a term mathematicians use to say that the solutions exist. The limit is the single angle approximation. Basically, you replace this angle between momenta of the neutrinos by an average over the entire ensemble, and call everything else, including that average, to be mu. And that problem, which of course is familiar to nuclear physicists as the problem that Richardson had solved a long time ago, it is exactly solvable. So that one, exactly solvable, and it was shown by Godin in France a long time ago. Of course, Richardson wrote down the solution, but Godin was the one who wrote down the solution in terms of the beta ansatz as shown there. And if you can solve these beta ansatz equations, you can write down not only the instantaneous energies of that problem, but also the instantaneous eigenstates of that problem. I don't want to really spend too much time on it, just to show you that the proof of exact solvability was given long time ago by Richardson and Godin, and our problem is quite similar to that. Two of the adiabatic eigenstates are easy to find in the single angle approximation. And these are the extremal states. That is to say, if, for example, all neutrinos are in the first eigenstate, first mass eigenstate, then they are all spin up, Well, if you have n neutrinos, they are all spin up. The third component of J is conserved according to this Hamiltonian. So Jz has to be conserved. So that tells you that you only have small j, the angular momentum quantum number of that SU2 equal to n over 2 surviving in that. So then you have a single SU2 algebra, and then you can easily write down the solutions. To find others take a lot more work, but these two external solutions are easy to write. Now, given that is the case, about 3 years ago, we looked at a initial thermal distribution with a temperature of 10 MeV of electron neutrinos. We took 10 to the 8 neutrinos distributed over 1200 energy bins and used the solar neutrino parameters and normal hierarchy. So if you do that, this is of course a adiabatic solution. If you start with the distribution shown on the top of the slide, where you have all electron neutrinos and no other kind, and if you let the system evolve, by the time, for example, they reach to Earth, the detector on Earth, you will see that there is a split. This is the so-called spectral split phenomenon. Below a certain energy, all electron neutrinos basically convert to the second mass eigenstate. Above that energy, all electron neutrinos remain convert to the first mass eigenstate. This is actually relatively easy to understand, and I will sketch it later in this. And this is the famous spectral split problem shown in by many others in this neutrino many-body problem, and it had been demonstrated many times. My goal here is to understand this problem, the many-body aspects of this problem, a little bit better here. Now let's talk about the distinction between mean field approximations and many-body approximations. A system of n particles which can occupy k states. Let's consider such a system. Here, k is the number of flavors, right? I mean, n is the number of neutrinos, and capital N neutrinos can occupy either 2 states, which are electron or muon, or 3 states, electron, muon, and tau. So in the exact solution, of course, for this many-body system, you have entangled and unentangled states, and the dimension of the Hilbert space is k to the power n. When you go to the mean field approximation, which of course is extremely useful and illustrates a lot of physics, you have only unentangled states, and the dimension of the diagonalizing space is reduced to kn, which is of course typically for a large n much smaller than k to the power n. So no wonder if we can get away with using mean field approximation to understand physics, we use it because it really helps us enormously. Now, in order to actually quantify the entanglement, I will use the von Neumann entropy. Von Neumann entropy is minus the trace of the quantity rho log rho, where rho is the density matrix of the system. If you recall from the quantum mechanics classes, for a pure state, the density matrix satisfies the property rho square equal to rho. Well, the density matrix for a pure state is ket times bra of that state. And you can see easily if the state is normalized properly, rho square should be equal to rho. Well, if you take that condition, rho square equal to rho, and insert into this von Neumann entropy equation, then you'll find that entropy would vanish. Von Neumann entropy would vanish. So for a pure state, the entropy would be 0. Whereas for a mixed state, rho square can no longer be rho. It typically is less than rho. And then in that case, the von Neumann entropy is non-zero. So a non-zero von Neumann entropy is a measure of your states being entangled or mixed states. So if you can calculate them, then you can tell if the mean field approximation is adequate or inadequate for that system. Now, we also introduced the polarization vector, and I'm going to assume in the rest of this talk, I only have 2 flavors. 3 flavors is possible, but a lot more complicated to write down the equations. So I have a two-level system for two flavors. Then the density matrix is basically a 2 by 2 Hermitian matrix, and it typically is parameterized in the form shown at the bottom of the slide. Here, sigma are Pauli matrices, and P are the real quantities that we call polarization vectors. And if you take that definition and insert into the pure state condition, you find that absolute value square of the polarization vector for a pure state would be 1, but absolute value of the polarization vector for an entangled state or a mixed state is less than 1. And that's yet another way of saying von Neumann entropy is 0 or non-zero. Now, so in order to calculate the von Neumann entropy, we will calculate the density matrix using some method of the many-body physics. I'll show you results that we obtained using Bader-Ansatz and Runge-Kutta methods, and I'll tell you a little bit about the tensor product methods that we use. So you calculate this exact polarization vector. As you can imagine, that gets harder and harder as the number of neutrinos increase. So we can, in practice, do it for at most about 15 to 18 neutrinos. And then once you do that, you obtain the reduced density matrix for one of the neutrinos. To obtain that, you basically take the overall correct full density matrix and trace over the degrees of freedom of all the other neutrinos except the one that you would like to calculate the entanglement entropy for. And that gives us the reduced density matrix. Using that reduced density matrix, we can write down the entropy, von Neumann entropy. And that, of course, the fact that von Neumann entropy is not 0 will tell us, if it's not non-zero, will tell us that that particular neutrino is entangled with all the other neutrinos. If it's 0, that tells us that that particular neutrino is not entangled with the other neutrinos. Now, I should point out that no matter whether you're dealing with pure state or reduced state, whether pure 2 by 2 density matrix or a reduced 2 by 2 density matrix, you can write down, of course, the polarization vector in that formalism where you define the polarization, density matrix in that formalism where you define the polarization vector. And using that, just take that and put that into the formula for the entropy, and you can write down the entropy in terms of the polarization vector. And as I told you, polarization vector absolute value is 1 for a pure state, and you can easily see that expression that when the magnitude of the polarization vector is exactly 1, then the entropy is 0. Now, here is our first calculation that we have done about 3 years ago. Basically, we took the neutrinos and we binned them in energies which are integer multiples of a principal energy, just for convenience, and we put 1 neutrino at each energy bin. So like on the top, I'm showing you the result we obtained for 9 neutrinos, and the many-body result and the mean field result are both shown. As you can see, as the number of neutrinos increase, there is a reasonable difference between those two. Now, in the bottom of the slide, I show you the entanglement entropy for each neutrino, entanglement entropy of the last neutrino in the series for each n. For like n equal to 2, it's the highest energy neutrino entanglement entropy. For n equal to 3, it's the highest energy neutrino entanglement entropy, and so on. And as you can see, that in the many-body case, the entanglement entropies for these neutrinos are not 0. They're small. Here, the assumption is we started with all electron neutrinos. They are small, but they're not 0. So the neutrinos, as they propagate, start getting entangled. Well, this result I had shown you was obtained with the Bethe-Ansatz method. Well, turns out the Bethe-Ansatz method has numerical instabilities for larger values of n. So we switched to Runge-Kutta for n greater than 9. But the Bethe-Ansatz method is quite valuable since it's an analytic, at least analytically manipulative. You can manipulate analytically, so you can obtain, for example, you can identify conserved quantities that you can use in assessing the validity of your solution for the Runge-Kutta or the tensor product methods. So we use the Runge-Kutta for neutrinos greater than n, and then we got results for neutrinos up to 16 or so that way. Here, I'm going to report results from Bethe-Ansatz and Runge-Kutta methods, and I'm going to briefly mention the tensor product methods at the end. So here is the distinction between the 2019 plot and our new result that we published last year. We can go to now up to 16 neutrinos, and as you can see, the difference between many body and mean field increases, and the entanglement entropy also increases as you increase the number of neutrinos. Now we have to understand this a little bit better. What is actually going on here? And in order to understand that, we actually looked at a case where we changed, for example, we first changed the mixing angle. The results I had shown you were all obtained with a small mixing angle. What if you increase the mixing angle? What happens? Well, there is an effect. And as you can see, on the left, you have a small mixing angle, and on the right, you have a larger mixing angle, basically representing the solar and atmospheric ones. But you can, of course, study this as a function of the mixing angle. So you can see that there is an effect. And what that effect is, of course, is something that we need to understand further. And let's look at the case when we look at the neutrinos with the energy at the split energy, the spectral split I mentioned. As if you then look at not the last neutrino in your bin, in your spectrum, but the neutrino which sits at the spectral split, then things change quite a bit, as you can see. So let's try to understand what this is a little bit. In order to do that, I have to go over a little bit what we obtain using the mean field results. In the mean field situation, the polarization vector satisfies the equation written there. Here, A, of course, stands for each neutrino. For example, W sub A is delta M squared divided by twice the energy of that neutrino. And remember, the polarization vector is nothing but the trace of J, the angular momentum operator. So Px is trace of Jx multiplied by rho. Py is trace of Jy multiplied with rho, and so on. In the main field case, of course, rho is relatively easy to write down, and you can write down these equations. And you can also show that B dot P is a constant of motion. What does that actually result in? Well, what we are interested in, adiabatic evolution. In the adiabatic evolution, basically, the polarization vector P of A should not be changing too much, should be changing extremely slowly. If it were not changing at all, that derivative would be zero. That means each polarization vector would be perpendicular to the B and also to the sum of them. Well, that means, of course, it is in the plane defined by B and the sum of all polarization vectors. Well, of course, that's not the case. it's adiabatic, but it's slowly changing, but the derivative is not zero. So then there is a component perpendicular to that. So you can write down the polarization vector basically in terms of these three vectors, the B vector, the sum of all polarization vectors, and B plus B cross P vector. Now, of course, these coefficients have to satisfy certain conditions depending on your initial conditions. So if you take that definition and put that into the equation on top of the transparency, you get the equation in the middle of the slide. And then you define capital gamma to be quantity shown there. And you can easily show, this is quite straightforward, that unless capital gamma is positive, the solutions for px and py exponentially grow. But we know that absolute value of p should be 1, so you cannot really have these exponentially growing solutions, so you only have an exponentially decaying solution as shown there. So there are these exponentially decaying solutions, and then you can basically write them down. In the mean field approximation, then you can see that these quantities that I called gamma x and gamma y, they precess around B with a time-dependent frequency. And then x and y components of the polarization vector also precess similarly while decaying due to the exponential terms. Hence, in the mean field approximation, exponentially, px and py tend to be very small. However, since p absolute value squared has to be 1, if px and py are going to 0, then pz squared should go to 1. So then allowed asymptotic values of pz in the mean field approximation are plus or minus 1. But now there's a constant of motion. The total PZs have to be conserved. It's fixed by the initial conditions. So some of the final PZ values will be plus 1, and some of them will be minus 1. And this is the spectral split phenomena in the mean field. As you can see, I show that here very schematically. Basically, as a function of energy, PZ can take sometimes the value plus 1, sometimes the value minus 1, and of course there will be a jump, and that is the spectral split that I had shown you earlier. And depending on the initial conditions, there may exist one or more spectral splits. The only constraint is that the P sub z, total P sub z, is conserved. And as you can see here, it has to be conserved. Now, what we find in the many body calculations is that the presence of spectral splits is a good proxy for deviations from the mean field. So here basically I'm contrasting the mean field and the many body results. I'm plotting P sub z. Of course, in the many body case, P sub z comes from the reduced density matrix for that neutrino. In the mean field case, since all neutrinos are the same, they are not interacting with each other. They all have the same PZ. And as you can see, at around the split frequency, the entanglement entropy is maximized. Entanglement entropy turns out is quite small away from the split frequency, but at the frequency where there is a spectral split, it is maximized, and eventually it goes back to 0 as you go away from the spectral split. And the probability of observing the first mass eigenstate, PZ, for the first mass eigenstate, then is a smoother change from plus 1 to minus 1. Now, this should remind you the behavior of the Fermi statistics at 0 temperature and finite temperature. Basically, what we are seeing here is the entanglement coming in because of the interactions between neutrinos. Now, this is a schematic result that I showed you, but now let me show you the results that we obtained by getting the by using the many body calculation. Here is a result. I assume that all mass eigenstates are electron neutrinos. All mass eigenstates are in electron neutrinos, and you have altogether 16 neutrinos. when I say all mass eigenstates and electron neutrinos, that means P1 is cosine square of theta, as shown in the red curve here. Well, you can see that the final result for the polarization vector for the first neutrino goes from +1 to -1. Well, actually here, I'm sorry, this is the probability, not the P sub z. Probability is P sub c plus 1 divided by 2. So it goes from 1 to 0. As you can see, it changes very smoothly from the value 1 to value 0 for probability and -1 for the polarization vector. Also shown here is the result you obtain from the mean field calculation. As you can see, mean field is a much sharper drop as compared to the many-body result, and also shown entropy, the blue line, blue dashed line. And as you can see, the entropy is basically, entanglement entropy is basically 0 as you're away, as you go away from the split frequency, but near the split frequency it maximizes, then it goes back to 0 again. Well, that was all electron neutrinos at the beginning. Now I still have 16 neutrinos in this plot, but I start with 8 electron neutrinos and 8 neutrinos of the other kind, typically considered as muon neutrinos, and I change here the mixing angle to be smaller. And as you can see here, there are 2 splits, not just one. There are 2 spectral splits in this case, and you again see the same behavior. As you go away from the spectral splits, the entanglement vanishes. Mean field result is reasonably correct, but as you get closer to the spectral split frequency, the many-body effects become important, as demonstrated by increasing entropy. Now, where do we go from here? So I want to actually give you a idea of what we can do after this point, because obviously n equal to 16 is still a small number as compared to the number of neutrinos that you get in supernova. So you would like to see if there is some sort of scaling in these results, for example, as n grows, and what kind of scaling, how you can explore the very large behavior. There are some results looking at the extremal states, but in general, we have no idea what happens to many-body effects as n gets larger. Of course, the folklore is that as n gets larger, many-body becomes more and more important, or more and more dominant. Mean field becomes more and more dominant, but you have to show that is the case in this problem. So the very first thing is to actually use a method that can go beyond the n equal to 16 or so. Runge-Kutta gets more and more difficult as you increase the number of neutrinos, because remember, the size of the Hilbert space is 2 to the n, which is for 16 neutrinos 2 to the 16. So that gets 2 to the 16 is manageable. One can do Runge-Kutta for that, as I had shown, but nevertheless, when you add 1 more neutrinos, 2 to the 17 is doubling that Hilbert space. Once you add 1 more, again doubling, so it's exponentially increasing. So the very first thing one would like to do is tensor methods efficient to go beyond these smaller numbers of n? Well, of course, you have to be careful, because in the tensor or matrix product methods, you're trying to reduce the Hilbert space into a manageable size that represents still the field's original physics of the problem. And you want to know that you succeeded in doing that. In order to do that, we actually use invariants obtained in the Bethe-Ansatz approach. You can obtain these invariants, which are equations of motion. You can only get them from the Bethe-Ansatz approach, but once you know what they are, you can use them in the tensor methods or the Runge-Kutta approach and so on to see. That one we finished. Actually, it's when I say we finished, it was on the archive yesterday. And the next step, of course, I'll show you a result from that. And the next step, of course, then using tensor methods to explore the scaling behavior. And of course, the most important question is in these tensor methods, you have to include the bond dimensions, and the fewer bond dimensions you have, the less calculation you're doing. Can you get away with smaller bond dimensions? Well, I can tell you from the paper we put out, and I'll show you a graph in a second, we put out yesterday, you need still a relatively large number of bond dimensions, even in the tensor methods. Well, if you have less than half of bond dimensions, which is less than half of, if the bond dimension is less than half than the size of the Hilbert space, then the results start deviating from the results that you expect. That we can check using these invariants. So you need basically a bond dimension which is half the size of the Hilbert space. Well, again, when you have 10 neutrinos, 2 to the 10 is your Hilbert space size. So that's still a sizable bond dimension, as you can imagine. And the other thing that one would like to check, of course, what impact we have of this in nuclear physics. So what is the impact of using many-body solution instead of the mean field solution in calculating the element synthesis? Because as I told you earlier, element synthesis is controlled by the neutron to proton ratio, which of course is controlled by the electron, neutrino, and electron anti-neutrino fluxes, and those fluxes change whether you use the mean field or many-body case. So that is something that we are looking at with Jilu Wang and Rebecca Sermon. We have a lot of progress, but there I don't have results I can show yet, but hopefully perhaps we can have some results in a month or so. So here is what I wanted to show you from the tensor methods. So we have done the calculation a number of times and looked at the computation times for a certain number of neutrinos. Here, n is the number of neutrinos that you put in the Hilbert space, and we looked at up to n equal to 24. Now, as you can see, the green circles are Runge-Kutta results. And as you can see, as one expects, for Runge-Kutta, the computation time increases very, very rapidly in days. So once you go beyond n equal to 15 or so, it's hard. We also looked at Lanczos algorithm, which of course is a popular algorithm in nuclear physics. And Lanczos algorithm is increasing a bit slower for larger n, but it's still increasing more or less exponentially. And then we show you the two tensor method calculations. One, the blue crosses is the initial state is all electron neutrinos. The other one, the black squares, is when the initial states are half electron neutrinos and half the other kind of neutrino. And as you can see, that is growing slower, not exponentially. So that actually gives us a hope that maybe these tensor methods can help us to delve deeper in this problem. Now, I would like to come to a finish. I don't know how much time I have at the moment, but almost out of my time. Let me just point out that calculations performed using the mean field approximation have revealed a lot of interesting physics about collective behavior of neutrinos in astrophysical environments. Here we have explored possible scenarios where further interesting features can arise by going beyond this mean field approximation. We found that the deviation of the adiabatic many-body results from the mean field results is largest for neutrinos with energies around the spectral split energies. In our single angle calculations, we observe a broadening of the spectral split region. This broadening does not appear in single angle mean field calculations and seems to be still much larger than was observed in multi-angle mean field calculations or using beyond the standard model physics. Now, this suggests that hybrid calculations may be efficient. Many-body calculations near the spectral split and mean field elsewhere. Of course, the boundary of the many-body versus mean field calculations is something we still have to understand by looking at the scaling behavior of n. And for that, hopefully, tensor methods will be valuable. And finally, we also observe a relatively strong dependence on the initial conditions, whether you start with all electron neutrinos or a mixed state. By mixed state, I mean half electron neutrinos, for example, and half the other kind of neutrinos. Well, thank you very much. And I will stop here and hopefully leave some time for questions.
Thank you very much, Baha, for a very nice talk. Lots of interesting ideas. So let's open it up for questions. Philomena, go ahead.
So Baha, this is a really nice exercise, but I was confused from the start about the motivation for this, because you have a very large amount of neutrinos, but do you actually know the density of the neutrinos?
Well, yes, we do, because I think the total energy released is relatively easy, because it's basically the entire gravitational binding energy of the pre-supernova star. So we know that the energy released is something like 10 to the 58 neutrinos in general. Well, it's 10 to the 59 MeV. And since we know the neutrinos from supernova 1987A observation and also from theory, neutrinos carry an energy of about 10 MeV per neutrino. That is something like 10 to the 57 or 10 to the 58 neutrinos. Now,
Okay.
of course, that is the total number of neutrinos emitted over a period of the order of seconds. And then, of course, as the neutrinos travel away from the protoneutron star towards the outer shells of the supernova, they get less and less dense. But in principle, we do know the density of the neutrinos under certain assumptions.
Okay, so that was one thing I wanted to clarify. And then the extrapolations to, so obviously you're not going to do 10 to the 58.
No, that's why we want to look at scaling.
And is it understood? Would you expect to have anything like some phase transition or things like that as these numbers increase in such a way that the calculations when n is small don't really port to the calculations when n is so large?
That's actually a very good question. And people looked at this not as n gets large, but as you go from the mass basis to the flavor basis. People looked at if they can see a phase transition in that case, because that's also not completely explored, since in particle physics, everything is done by one body, so you don't have to worry about these phase transitions. And they found that there are hints of BEC to there are hints of a phase transitions from a Bose-Einstein condensate to a supersymmetric state, to a superconducting BCS state. But those are just hints. So that's a relatively unexplored area, I must say. And there are a lot of things that one has to do there.
Okay, well, thanks so much. Such an interesting topic.
So are there other questions? while we're waiting, perhaps?
Ask a question?
Okay, sure. Yeah, go ahead, Wolfgang.
Yes. Okay. I don't understand very well this transition to this very large
So,
sound.
Wolfgang,
because-
I cannot really hear you. Is it possible to get closer to the microphone? Sorry.
Is it better now?
A little bit better.
Okay, I will speak louder. It's to have entanglement, the particles must be governed by the same wave function, I think. And well, if you go to bigger numbers, all these all described by the same wave functions, because if they are described by independent wave function, if there's scattering and interaction, you will lose the correlations.
Sorry, Wolfgang, it was hard to hear you, but if I understood right, you're asking the effect of the scattering as.
Yeah, well, scattering is one type of interaction that is non-coherent. And so it destroys entanglement. And in these big numbers, I don't see what will be coherent and what will be incoherent.
Well, as I said, I'm sorry, I really cannot hear you very well, but if I understood you right, we are ignoring the collisions of neutrinos with other particles. This is in the region, this collective effect is in the region where neutrino density is so high that the Hamiltonians that describe interactions with other particles is very small. So we are ignoring those. Of course, in principle, those you have to include. But near the protoneutron star, the interaction with other particles go like, you have to look at their cross-section, go like the square of the interaction strength, which is the Fermi strength, G Fermi square. Whereas the effect that we are looking at, the coherent forward scattering of neutrinos from one another, is an amplitude effect. So it goes like G sub F. So given the fact that density of neutrinos is very high, much higher than the density of all the other particles, and the collisions are suppressed by a factor of G sub F, we are ignoring them. But you're absolutely right. As you get closer to the region at other parts of the star, either supernova or merging neutron stars, then those collisions become very, very important. I don't know if I understood your question right. I couldn't really hear it, but is that satisfactory?
Yes, I think it's more or less satisfactory. But, for example, there were recent experiments of scattering of gammas from positron annihilation. And in these experiments, you saw that you lose by scattering the coherence effect, so entanglement.
Yeah, now I hear you much better. That's nice. Yeah, I see. Yeah, indeed scatterings would obviously break the coherence. Absolutely.
Okay, there's a question, Jilin, why don't you go ahead?
Hi, I have a question. Do you assume the particle neutrinos are Dirac particles or Majorana particles? Do you assume that?
For this calculation, that distinction does not matter as much because the mass effects, I mean, that distinction comes through the mass of the neutrino, right? And but since these neutrino energies are so high, in the neutrino-neutrino interactions, any contribution coming from the mass is basically negligible.
Oh, so you're saying that basically, even for Majorana particles, the self-annihilation rate is so low that is not relevant.
Exactly.
Okay,
So
thank you.
that's the catch. Now, if you have, there's a caveat. If you have very strong magnetic fields inside the star, and also if the neutrinos carry magnetic moments, the thing can be different. But we're not looking at that case yet.
Okay, thank you.
So Baha, actually, I have a question. So this is a really interesting many-body system you're studying. So if we consider the two-flavor single angle case, so I'm actually looking at your paper that was on the archive a few days ago in equation 1. So that interaction term is j omega dot j omega prime summed over all omega and omega prime not equal, right?
Right.
So couldn't we just rewrite this using this difference of the total angular momentum squared times 1/2 minus 3/4?
Of course.
Yeah, and
Sure.
then the other term could be perturbation against that, and you could solve it using.
That's the catch. It's not small. The other
Okay.
term is not small because
Mhm.
you see, there are two terms, and these two terms are changing as the neutrinos travel from the center to the surface.
Mhm.
Near the center, near the neutron star, the second term is much larger.
Mhm. Mhm. Gotcha.
But by the time neutrinos make it to the surface or near the surface of the star, the first term is much larger.
Okay.
So
Right.
it's very difficult to use anything perturbative in that sense because.
Okay. Thanks, Baha. Are there any other questions?
May I ask one question?
Sure, Vladimir, go ahead.
Is the system of neutrinos superfluid?
Perhaps, but as I said, you're asking if the neutrino is a superfluid, right?
Yes.
That is still not completely clear in the following sense. People, as I said, looked at the BEC to BCS transition, but it was not very conclusive. It looked like consistent with it. So whether one can actually consider the many-neutrino system as a fluid is still a relatively open question, but that's a very good question to explore.
Thank you.
Okay. Any other questions? If not, then let's thank Baha for a wonderful talk and a great discussion. Thank you so much, Baha.
Sure. Take care.
Yeah, take care.
Enjoy being here.
Yeah, our pleasure.